Welcome, StorPool. Welcome, Venko Moyankov. I'm really excited about the next talk. We will learn a lot about KVM and how to achieve the best performance out of KVM. Venko, your stage.
Hallo und willkommen. Wir freuen uns, heute mit Ihnen zusammen zu sein. My name is Yvette and I'm the marketing manager of StorPool Storage. And at StorPool, we are very happy to be together with you today. We're happy and also very excited to be part of the Data Disrupted Conference, one of the most interesting conferences focusing on IT technologies, storage, virtualization, and building different kinds of IT stacks. Together, we will present the topic Achieving the Ultimate Performance with KVM. And the speaker of this talk is Venko Moyankov, who is a solutions architect at StorPool Storage. Hello, Venko.
Hello everyone. My presentation today is about KVM and how we get the highest performance out of our KVM hypervisors. My name is Venko Moyankov and I'm a solution architect at StorPool. A few things about me. I have more than 20 years experience as a network and system integrator, mainly in the telecom sector, working for telecoms and system integrators that work for telecoms. I've been building and managing and operating different infrastructures, but basically the job that I did was basically networking and system administrator. And a few words about StorPool. At StorPool, we do high-performance scale-out software-defined storage. We started almost 10 years ago with first commercial deployment back in 2013. We are based in Sofia, Bulgaria. StorPool is mostly used for virtual disk for KVM virtual machines, but it's also used for storage for bare metal Linux servers running containers, also used with VMware, Hyper-V, Zen server. We have a deep integration with OpenStack using Cinder driver. We can provide persistent volumes for Kubernetes using CSI driver. We have integration with the Cloud Stack, OpenNebula, ONAP. Basically, we cover the entire KVM family of hypervisors and orchestrators. In this presentation today, I'll try to share some of our experience with KVM hypervisors and how to optimize them. This is the experience that we've built through the years together with our customers and partners that we built many cloud-based solutions for our customers. So I hope that this information will be useful for your new projects. Better performance of hypervisors gives better application performance. This means lower time to load pages, lower time to build your software project, lower time need to execute a query, and this leads to happier customers. If you are running public cloud, this means better user experience, faster time to load pages. If you are running private cloud, it could be a faster completion of continuous integration tasks and software builds and so on. But performance also have a pure economical measurement. Better performance means lower cost per delivered resources. You can have more tasks run, more virtual machines on the same hardware with the same OpEx and CapEx. So we'll show today 4 different aspects of how you can optimize your KVM hypervisors. We'll start first with hardware, selecting the hardware that best fits your need. Then we'll go through the some tunings of the operating system, CPU and memory settings, and we'll cover 2 of the most important components of your cloud stack. It's networking and storage, and what optimization can be done on these 2 parts of your cloud. So when you're selecting hardware, first you need to answer a question: what you're optimizing for. So there are two different optimization strategies here. The most common optimization strategy, this is to get the lowest cost per delivered resources or the maximum resources for a fixed cost. And so an example of this strategy would be the lowest cost per virtual machine with a certain parameters. And the other optimization goal is more unusual, to get the best possible performance for a given hardware or for a single thread performance. This is the case usually when you have very specific applications that you need to run at the maximum speed, and the cost is a secondary factor, or when the licensing fees are very high and the hardware cost is not very important in this case. So this could be, for example, if you're running, let's say, Oracle database server, where the licensing cost is the primary factor. So when you're optimizing for cost, you have to select between different CPUs, different amount of memory, different hardware architectures. Typically, you start with selecting a CPU. Selection of CPU is usually not an easy task. At the moment, only Intel, with their latest generation of server processor, Xeon Scalable second generation, has more than 60 different CPU models. And if you add to this number Xeon E-series processors and AMD EPIC processors, then we can get more than 200 processors to select from. So to help with this task, we have developed a spreadsheet that can calculate the total cost of in this total cost, it's included not only the cost of the CPU, but also the cost of the entire server. And you can tune different parameters like amount of memory, but not only the server, you can also add other operating expenses like power cost, the cost of the rack space, operating and maintenance, licensing costs, and deployment costs, and so on. So with this spreadsheet, can give you the total cost through the entire life cycle of the server per core. With different input parameters, you can get different CPUs at top that gives you the best cost. This is an example with a certain parameter, certain sets of parameters, and you can see that you have a different parameters, for example, for a best cost per CPU core, or another CPU gives you best cost per gigahertz. The typical top results are Xeon Gold 5220 if you're looking for best cost per core, and if you're looking for a top performance, then you may want to select Xeon Gold 6230R that works at 3 gigahertz, not at 30 gigahertz. So keep in mind that this is not a recommendation for specific models. This is just an example what could be the best choices for a specific set of input parameters. This spreadsheet is available online, so if someone needs it, just let us know, drop us a note on our email or on our social media. You'll see the contacts later. And some examples for AMD processors that are often at the top of the list. One interesting example is the EPIC 7262 with only 8 CPU cores. This is not the typical choice if you are building hypervisors, but if you are looking for a system that needs a maximum ratio of I/O bandwidth per core, or maximum layer 3 cache per core, this CPU provides a very good ratio for this. So it's a good choice when you're looking for applications that needs a lot of I/O. Selecting the best fit for chassis and for chassis form factor again depends on many parameters. Factors such as cost of rack space, the maximum power per rack may lead to very different chassis. If your rack space cost is significant, then probably you go to a high-dense solution like this one on the rack, where 4 nodes can fit into rack units. On the other hand, if you have a rack limit, power limit for the rack with only 6 or 4 kilowatts per rack, then the best solution will be very simple chassis like shown here on the left, like one server in 2 rack units, no any fancy stuff here, very basic chassis, but it will give you best cost per server. So advice here is don't select the hardware before you know all the costs and all the limitations that you have in your data center. Once we have selected our hardware, we need to tune the system for best performance. The first step that we suggest is to update the BIOS and the firmware of the hardware with the latest available versions. This may have a significant impact on the overall performance. So use the latest version unless there are some known issues that will affect your specific use case. Understanding power management is very important, especially C states and P states of the CPU. So you can tune your CPU mode of operation that fits to your workload and to your needs. You need to answer the question what you are optimizing for. Whether you are optimizing for maximum throughput, this means the maximum work to be done for a certain time, or you're optimizing for maximum burst performance. This means maximum speed for a short period of times, or maybe for lowest latency of the application, or maybe you're optimizing for power usage. So there are different settings, and when you're doing optimization, you need to answer what you're optimizing for, and you need to test with your specific workload, not with just a raw synthetic test that will give you some numbers. So different optimization can give very different results. And again, think here at rack level, not at a single server level, and measure with your applications and with your workload if possible. Next, we'll see what are the optimum settings for the CPU and memory in different use cases. There are a lot of good papers on internet for optimizing and settings of QEMU and the operating system for virtualization. We suggest to have a look at these links. So this presentation will be available on our virtual booth. Check out there and get the presentation with the links there. So these are very useful papers. The first one, it's from Red Hat. It's regularly updated and has a very good advices on how to optimize QEMU. I will not repeat all of them here. But considering all these papers, there is one thing you should be aware of. There is no single setting that will work best for all type of workloads. So don't trust this recommendation blindly. Always do your own benchmarking with at your environment, with your servers, with your software, with your applications and your workload. So you have you may have a very different results compared to the benchmarking that is done in a different environment where the recommendation was written. So general rules are to use latest versions of Linux kernel and QEMU, but not use the very latest version from the upstream project that are not widely tested. So our experience says that a good compromise is the package from Red Hat Enterprise Virtualization that's repackaged by CentOS. It's QEMU KVM EV package. It has a very well balanced default settings, and in most of the cases, the default settings of this QEMU binary works well. When we're talking about optimizing the settings for the operating system, there is one very useful tool called TuneD. It's available in most Linux distributions, and this comes with a set of different profiles. The profiles that would be useful in your case is virtual guest and virtual host. Again, these profiles repeat most of the recommendations in the Red Hat paper. However, it may need you to fine tune it for your specific deployment, and you need to benchmark it to make sure that the settings work best for your case. So optimizing for CPU utilization has two different approaches. The typical one is to have a high CPU oversubscription, and this is because the typical VMs, virtual CPUs are mostly idling. This allows you to run much more virtual machines and virtual CPUs than you have on the physical server. And this will give you the maximum resource per physical hardware that you have. This is the usual practice if you have a public cloud. This is the usual practice for many private clouds and for many different deployments. If you do this, then you most probably will need to enable hyperthreading. If you're running multi-socket servers, you need to pay attention on the NUMA locality. The operating system on the host does a good job to route the tasks on the proper CPU core, but sometimes you may need to manually set this. The more unusual approach here is if you have to dedicate physical CPU for every virtual CPU. So this is the case if you need to get the maximum possible performance out of a virtual CPU, and if you can for different reasons, or maybe if you are restricted by some software licenses. This practice is usually combined with CPU pinning. CPU pinning means that one physical CPU will be used exclusively for a certain virtual CPU. CPU pinning has some advantages. This means that virtual CPUs will be not switched between different physical CPUs. That will help a lot with preventing cache poisoning and will give you additional a few percent of performance. On the other hand, CPU pinning would not enable you to do live migrations, and of course will not enable you to do any CPU over provisioning. So when we're talking about CPU over provisioning and over provisioning in general, it is very important to make a difference between oversubscription and congestion. So oversubscription, there is nothing bad with this. Well-designed and well-done overprovision usually does not have a negative impact on the overall performance or on the end user experience, while at the same time we will give you much more efficiency on resource utilization. On the other hand, congestion is the thing that that has a negative impact on the user experience and on the performance. So you can have, for example, very low average load and still have a congestion, or you can have a high load on the CPU with no congestion at all. So what you need to do when you have any oversubscription is to measure carefully the congestion and to monitor it very closely, the congestion of your system. We're not talking only about the CPU, but for any resource that is oversubscribed. So when you're doing this for CPU, the good way to measure the congestion is using statistics from provided by the host kernel. It is available in the proc shedstat file in the proc file system of the hypervisor. And there are many, a lot of numbers there. The number that you look for shall say something like waiting time on the queue. This is marked here in yellow. In different kernel versions, it's at different positions, so check your kernel documentation. Also, pay attention here that the documentation says it reports this in milliseconds. It's actually in nanoseconds, not in milliseconds. So this is a counter that shows the time that the task spent in the waiting queue, waiting for a physical core to be made available to execute this task. In ideal case, you don't want to have any increments of this counter. This means that there is no congestion, and for all the tasks, there is always available CPU to serve them. So one example here, this is the numbers from one production cluster. We are measuring this number, and this number is normalized against the number of available CPU cores. So we have a certain, here we can see we have a low average wait queue time, so a low average congestion. However, there is a regular, every 5 minutes, there is a short burst, short peak in the congestion, where you can see it can get up to 200%. This means that at this moment, there are 2 tasks waiting on the queue while the third task is executed by the CPU. This is caused because at a certain time, a lot of virtual machines simultaneously request CPU resources to execute tasks, and this is actually the cron jobs. However, cron jobs are usually not time critical, so this is not an issue, but you need to keep your attention on the congestion. Memory optimization. Again, there are 2 different approaches. The typical one is to use a dedicated physical memory for the virtual memory, in contrast with the CPU, where you have an oversubscription. With a memory, the typical one is to have no oversubscription for the memory. The more unusual optimization approach is to oversubscribe physical RAM, but this is something that we see at a very small number of projects, probably below 10% of total clouds. When you are doing a dedicated RAM, you can use huge pages. Huge pages is something that we strongly recommend if you're able to use it. Enabling huge pages can give you a couple of % additional performance improvement in many workloads. However, there are known certain workloads that don't work very well with huge pages. So again, we recommend to benchmark with your specific workload. if you're doing memory over subscription, there are two possible techniques: ballooning and kernel same page merging. Ballooning is the legacy one. It required cooperation from the guest, and it is most often used in private clouds where you have a control over the guests. The more recent one is kernel same page merging, or KSM. This actually detects kernel pages that have same content and merge them in a single physical memory page. This will reduce the actual physical memory used. However, this is a trade-off between the memory used, memory consumption, and CPU utilization. So in certain workloads where you have a lot of duplicated and a lot of memory with this duplicated content, this may help a lot. In other workloads with a lot of dynamic memory content, this may have a negative impact on the overall performance. The next thing is networking. There's a lot of stuff to be optimized on the networking subsystem. So when you're designing your virtual network, you have two very different approaches. So you can use virtualized networking. This is the most typical decision, and you can have you can use PCI Passthrough and physical networking for your virtual machines. So this is a more unusual approach. Pass-through networking will give you the best possible performance because there will be no any virtualization overhead, or almost no overhead. But on the other hand, you will not be able to use any of the advantages of virtual networking. So virtualized networking can use different technologies. The first available technology historically was hardware emulation. So you have a certain hardware emulate in software by the hypervisor. The typical choices here are a Realtek 8139 or Intel E1000. This gives a very low efficiency and very high virtualization overhead. So we recommend, if possible, avoid hardware emulation at any cost. Much better results you can get with para-virtualized drivers. With these drivers, hypervisors emulates a virtual device, virtual device, that is optimized for use in a virtual environment. You need to have virtual drivers in your guests. For all Linux guests, virtual driver is installed by default, so there is no issues with this. If you're running Windows guests, then you need to install these drivers as an additional step. And there are two ways to run virtual net, regular virtual, or using vHostNet interface. Regular virtual is using networking and emulation in QEMU process, while vHost interface provides much more efficient interface for communication between the virtual machine and host networking. And when you are doing the networking, again, you have two choices here. You can use three actually. You can use Linux Bridge for virtual networking on the host, or you can use Open vSwitch with in-kernel switching, or you can use Open vSwitch with user space switching using DPDK library. So we'll go with in more details with these different options here. So now I completely skip hardware emulation. because this should be avoided if possible. We'll consider first how virtual.net works with a virtual.net device emulated in the QEMU process. So this is using this configuration is using shared memory to send and receive packets from the virtual machine and to communicate with the host. There is a virtual.net driver in the guest and the shared memory block that contains input-output buffers that is shared with the QEMU process. So when the virtual machine wants to send a packet, it places the packet content in the shared buffer and signal the virtual device, virtual.net device, through executing VM exit for actually executing VM exit and switching the control to the QEMU process. This actually involves multiple context switches. So first there is a context switch from the virtual machine to the KVM in the host kernel space, and then KVM switch the execution to the QEMU process that runs in the host user space. Then the QEMU process this request and send the data using a standard tap interface. So sending this data over tap interface involves another context switch. It is to process the data in the kernel space. So from this step, typically Linux bridge process the data and send the data over the physical network interface to the external network. Then the QEMU process signals back the virtual machine that the request was completed. It does this through switching through the KVM, so one more context switch, and from the KVM it executes a virtual interrupt to the virtual machine, so one more context switch. So this means that processing a single packet involves at least 5 context switches. This adds a significant virtualization overhead and a reduction in the performance. It's times better than hardware emulation. To optimize this process and optimize the virtualization, vHostNet interface was developed. This allows shared memory to be used directly between, and memory to be shared directly between the guest virtual machine and the host kernel, and QEMU process to be completely bypassed. So QEMU process here operates only on the signaling plane, while on the data plane it's completely bypassed, and transferring of the data and processing of the packet involves only 2 context switches when the data is put on the buffer and to signal the KVM and the host kernel that the data need to be processed, and to signal back the virtual machine that the request is processed. And even these 2 context switches are optional, so both the driver and the vHostNet interface can be configured to work with in a poll mode, where they regularly check shared buffer and they do not need to signaling the other party, so there is no context switches. Also, allowing this interface, enabling this interface, this allows to enable Linux bridge 0 copy, so you can do the entire packet processing without any copy of the memory regions. This mode of operation is default for many settings and for many deployments with libvirt. So most probably you're already using this. You can check this if you are looking, if you have in the kernel vhost threads executed. So for every vhost interface, there is a dedicated vhost thread in the Linux kernel. The next option is a variation of the previous one. This is vhost interface, but this time run at the user space. It's called vhost user. So like in the previous case, there is a shared memory between the guest virtual machine and another process now running in the user space of the host. In our case, this is Open vSwitch with DPDK. So Open vSwitch through this shared memory has access to the network buffers of the guest kernel. Through using a poll mode driver, this part of DPDK library, it can constantly check these buffers and can also send the packets, routed packets, and send them directly to the physical network interface without involving any operation in the kernel host, in the QEMU, or in the KVM hypervisor. So with this configuration, the guest virtual machine can send and receive packets with the help of the Open vSwitch process without involving a single context switch. This is the best possible configuration in terms of context switches and overhead. It does the entire networking with zero copy. However, it requires a separate process and a dedicated CPUs in the Open vSwitch, so some dedicated resources to do the virtual networking. Also, keep in mind that Open vSwitch might not perform as well as Linux kernel bridge in some workloads. So some workloads may work better with Open vSwitch, other workloads may work better with Linux bridge implemented in the kernel. And the last scenario that we'll see is PCI Passthrough. So in this case, the physical network controller is directly accessed by the guest virtual machine. So in this case, in the virtual machine, we have a network driver for the specific controller. So you don't have any virtualization here. We don't have any additional overhead of the virtualization. And the virtual machine is using PCI Passthrough technology to directly access the physical devices. The disadvantage of this technology is, first, you cannot use any of the features of virtual networking. You cannot use, for example, firewalling, virtual routers, filtering, load balancers, and other functions provided by the virtual networking. Live migration of virtual machines is not possible because they have a direct connection to the physical hardware. There is no control. You cannot apply any control from the host on what actually the virtual machine is doing with the network. You can share one physical device only if the device supports SR-IOV and if your hardware platform supports SR-IOV. SR-IOV is a technology to virtualize physical PCI devices and to present them as a virtual PCI devices. So one comparison that we did in our lab between different technologies. This is the round-trip latency between two virtual machines running on the same host. We exclude any physical network and physical network interface, so we can isolate and exclude the impact of the physical network. So we are measuring here only virtual networking and routing and switching in the kernel. So the lowest performance is with emulating physical hardware. You can see the round trip time is 140 microseconds. The best one is 10 times faster. This is VirtualNet with vhost user using Open vSwitch DPDK. And all the processing is done in the user space without context switches. And the other two options are in between them. You can see a single setting can change the performance with several times. So with different technologies, the CPU load is moved at different parts. So when you are running virtually on a device in the kernel, you can see there is a thread in the QEMU that handles all this workload. So even if you do not see this processing this workload in the virtual machine, there are some resources busy processing the traffic. In this case, this is a thread in the QEMU process. If you're running a vhost net, then this is a thread running in the kernel. So the QEMU process, there is no additional overhead in the QEMU process, but there are still some resources busy in the kernel. And if you run vhost user, then there is a thread in the Open vSwitch that does the network processing. So pay attention here and allocate the enough resources on the correct location where you actually need to process your networking. So more details on virtual networking and vHostNet, Open vSwitch are available at these links here. And the last thing that we'll discuss today is storage and virtual storage. So when you're optimizing for the storage, again you have two different strategies. Like in virtual networking, you can have a virtualized storage, or you can have a full bypass and use physical storage devices directly from the virtual machines. When you're using virtualized storage, you can have all the features that the virtual storage provides. You can have live migrations, you can use team provisioning, snapshots, storage-based backups. So basically all the features that your storage system provides. You can have high availability. On the other hand, if you have full bypass and using a physical storage device, you get the best possible speed, but you have speed only. You cannot have high availability. You have to deal with data redundancy by yourself. You cannot have live migration and so on. So in most of the cases, if you are using virtualized storage, you have to set your virtual machine with some parameters that work best for most of the cases. So we suggest to try with this first, and then to optimize starting from this baseline. So first, disable cache on the host. You don't need the host and the host operating system to cache IO traffic, because they're already cached in the guest. So use direct IO. There are two different ways and two different libraries to use IO: Linux native IO and POSIX IO. We recommend use Linux native IO. When run virtio, there are two different drivers and two different modes that you can expose to the virtual machine: virtio block and virtio SCSI. Virtio block is visible in the virtual machine as def VDA device, while virtio SCSI is visible as a SCSI device like def SDA. So we recommend using virtio SCSI, although it may have a few percent lower performance, maybe 1 or 2% lower performance than virtio block. However, it supports many SCSI features. It's a full SCSI device, and you can use, for example, with virtio SCSI, you can use discard functions that can help you a lot with efficient use of the storage, and can give you can gain additional performance and capacity. with virtuosity, we also recommend running multi-queue. Multi-queue allows to have a separate queue for every virtual CPU. This gives you additional performance. We also suggest to enable IO thread. Don't mistake this with IO equals to threads. IO thread means to dedicate a separate IO thread in the QEMU process and this thread to process all IO requests instead of the IO requests to be processed by the same thread that are used by the virtual CPUs. So dedicated IO thread will typically gives better performance and better resource utilization. If we need for absolute top performance running NVMe devices, then you may select SR-IOV and directly access NVMe devices from the guest virtual machine. So this gives you the best performance and lowest possible latency. But again, with all the limitations that we've discussed. Virtualized network with a Virteo, just like with a network, has two possible interfaces. The classical one, when the IO are processed by the QEMU, involves multiple context switches, much like with virtual networking. So a single IO request requires context switch from the guest kernel to the host kernel, back to the QEMU to this IO to be processed. Then QEMU again switch to the host kernel to process the actual and to access the actual storage device, physical storage device. If you're using vhost interface and especially vhost user, you can skip all this and using shared memory with a proper storage driver on the host, you can have a processing of the storage request without a single context switch. This gives you minimum latency and maximum performance. Unfortunately, there are very few storage systems that supports vhost interface. So this is an example how StorPool does this. We have a KVM virtual machine. We have a process on the host that implements the host interface. So there is a shared memory between two, and StorPool process can directly access IO buffers of the virtual machine. And using the technology similar to DPDK, it can send data over the network without involving a single context switch. On the server side, we are using the same technology. So on the server side, for example, this server instance received the data from the networking from the network without any context switch and directly access NVMe device bypassing host kernel, again without context switching. With this technology, we can ensure minimum latency. When we are measuring your storage, when you're optimizing for performance, be very careful what actually you are measuring. There are a lot of benchmarks available on the internet. There are a lot of benchmarks that you get from your storage vendors, but most of these benchmarks have nothing to do with the real workloads and with the real performance. So the benchmark that you need are the benchmark of your application using the storage system in your environment. Our recommendation is, when possible, always use your application, or if not possible, try to emulate your workload as close as possible. Do not do just a synthetic test. Synthetic tests can give you a very different results that are not related to the actual performance that you get in production. So one brief explanation of this. So every system, including the storage system, have such a profile. The latency of the processing the request depends on the workload. The higher load is, the higher latency is. Until you get to a certain point, this is the limit of the performance limit of the system. When increasing the load will not give you any more work to be done. It will just increase the latency. So in ideal case, you would like to operate your systems at this point where you get the lowest latency. In some cases, if you need to utilize the full capabilities of your systems, you may run your system at this area here, and you are close to the maximum of the capacity of your system. But if you go behind above this number, then you will not get any more work done. You will have only increased latency. Unfortunately, most of the benchmarks are done at this point. So there are no relations with the results that you will get where you typically will operate your system here or possibly here. So these are the real measurements from a real system. And the numbers here are showing what is the capabilities of the systems, how many IOPS it can handle. Usually you will not run your system at these numbers. Usually you run your system at these numbers. So if you're running here, for example, if you're running a system with and your workload is, let's say, 500,000 IOPS or even 1 million of IOPS. So does it matter where actually this number is, whether it is on 2 million or on 5 million? So what really makes a difference is what is the latency of the operation at your workload. So I hope with this we covered most of the aspects of how you can optimize your KVM hypervisor for your cloud.
Thank you, Venko. The presentation was really good, and I'm pretty sure that you gave practical advices and interesting information for people who would like to improve the performance of their infrastructure. On the screen now, you can see the social channels where you can find StorPool. We post regularly interesting technical content, advices, white papers, and yeah, basically all kinds of technical things which you might find interesting. So don't hesitate to follow us on the social channels. As we said in the beginning, we are very happy to be part of the Data Disrupted Expo, so don't forget to visit also our virtual booth. We have interesting information on the booth which you can download. We will also put the slides from Venko's presentation on our virtual booth, and they can be downloaded from there. And also we have a white paper about migrating to KVM. So if you are just planning your migration to KVM based stack, you might find this quite useful. And thank you for being together with us for this presentation. You can contact StorPool Storage at info@storpool.com, or you can maybe personally write a message to Venko if you have any questions based on the presentations to venko@storpool.com. Thank you for being with us and have a nice virtual expo. Bye.
Thank you very much. This is so nice. I guess we should ask Yvette next time for doing moderation for all of our talks. She does such a nice job. So yeah, thank you for the interesting presentation. For me, I take with me, you can save iron, but you have to deal with performance then. Yeah, my audience. Yeah, you can save iron, but you have performance issues maybe, but you can do some magic to increase performance on virtual machines with KVM.